In professional engineering environments, the practice of loosely prompting an AI to build a feature and hoping for the best is failing at scale. The standard iteration loop usually looks like this. You write a short prompt, wait for the AI to generate the code, run it locally, hit an inevitable error, and then prompt the agent again to fix it. This cyclical feedback loop is highly effective when you are writing a small, isolated script. But when applied to a complex, multi-file codebase, it collapses. The primary point of failure is a lack of shared conventions. When multiple developers and agents modify a repository without a strict framework, the internal architecture begins to fracture. You might review a data pipeline and find 5 different methods for executing machine learning model training inside a single dbt workflow. The agent simply forgets the architectural decisions it made an hour prior. The root of this problem is that large language models are stateless. As your chat history grows, the agent experiences context decay, losing track of the early instructions that dictated how the project should be structured. Achieving reliable leverage from AI requires engineering an external, persistent state that survives these inherent memory limitations. Spec-Driven Development is a formal framework designed to solve this decay by externalizing the project's logic. The operating principle here is decoupling. You physically separate the specification, the documentation explaining what you are building and why, from the actual implementation, which is the code itself. This diagram illustrates the shift in responsibility. Under this framework, the human developer focuses on architecture, system design, and establishing strict constraints. The AI agent functions as a syntax engine. Its only job is to execute the architecture provided to it. By dividing the labor this way, developers capture the speed advantages of AI agents while maintaining rigorous control over the quality of the software. To build workflows that function reliably, engineers must stop treating LLMs as conversational partners. A lack of memory is a system design problem, and you solve it through external documentation. The first practical step of spec-driven development requires you to establish the project's constitution. This constitution is the permanent memory drive, establishing rules across 3 documents before coding begins. The mission document stores high-level goals, the tech stack file logs core architectural dependencies, and the roadmap dictates execution, breaking the project into sequential phases. You don't write these from scratch. You draft a brief initial vision, and an LLM generates the initial structure of these files for you. But human intervention is mandatory at this stage. You must review and refine these documents to resolve any ambiguities. Take the fitness application Trainlytics. When the developer specified that the app must support both desktop and mobile devices, the agent updated the tech stack to include authentication and altered the roadmap to prioritize a secure login phase. A version-controlled constitution aligns the developer's intent with the actions of the agent. It ensures both are reading from the same architectural truth. Once the foundation is set, you move into active development. This requires isolating the next phase on your roadmap into its own feature directory. Every single feature goes through a repeating cycle: plan, implement, and validate. If we expand the plan step for a feature, we generate 3 new files: a structured task list, specific functional requirements, and criteria for success. For the implement step, you instruct your IDE agent to read only that specific plan document and execute the tasks exactly as written. During validation, the agent stops coding, and the human developer steps back in to review the work. In this case study, the developer spent this time verifying the core business logic and checking that the data outputs were accurate, rather than reviewing front-end syntax. When an implementation fails a test, you will feel the urge to simply drop the error into the chat and ask for a quick fix. You have to resist that shortcut. To maintain the system, you must update the specification documents with the correction and force the agent to rework the code based on that updated spec. Treating the markdown specification as the absolute source of truth, never the chat history, is what gives this framework its resilience against regressions. After successfully merging a feature, there is often an impulse to immediately begin coding the next one. Spec-driven development counters this with a required replanning phase. This is a deliberate pause to review the roadmap and verify that the application's trajectory still aligns with the constitution. Without this pause, you risk spec drift, where the actual codebase outpaces the documentation and the agent's contextual foundation begins to fail. You prevent this by formally updating the roadmap file to reflect the work completed and generating a changelog to establish a clear project history. To maintain this discipline, developers are automating these strict workflows using command line tools like GitHub SpecKit. While manual documentation works, automated tooling can enforce architectural concerns like user interface consistency and testing standards without requiring constant human prompting. Replanning and tooling are not administrative overhead. They're the maintenance mechanisms required to keep an AI agent's external state intact. The result of the Trainalytics project was a functioning data web application built through a disciplined specification-first workflow. The entire greenfield project, from the initial idea to a working product, was completed in 4.5 hours. This full-stack deployment was executed by a data professional who did not have prior expertise in the underlying front-end technologies. The experience of building Trainalytics highlights a shift in where a developer applies their effort. By offloading the syntax generation to agents, the human's time was reallocated to strategy, architectural decision-making, and the rigorous orchestration of the system. This suggests that natural language is becoming a viable interface for programming at a professional scale. While English may be the interface, building robust systems still requires the same structural discipline